Hey everyone, I'm here to help you with your square root curve corrections for the Unit 8 Atomic Structure Summative. So take out your test. Hopefully this is helpful. All right, we're going to start with number 2, a little bit of review. So we are looking for Rutherford's experiment where he bombarded atoms with alpha particles. And what he noticed was that alpha particles, instead of going straight through the atom like he predicted, some of them were deflected and bounced back, which told us that there must be a positive charge in the atom concentrated in a small central region, which we call now the nucleus. So Rutherford gets credit for discovering the nucleus. And next, we're going to look at questions 3 and 4. So when I do all of these, anytime I'm looking at periodic trends, I always look at the principal quantum number or the energy level. So nitrogen is in the second row. It has the energy level of 2. Neon is in the second row, energy level of 2. Magnesium has the principal quantum number of 3. It's in the third row. And rubidium has 5. Okay, and then we're going to look for protons only if there is a tie. So we have so for these two right here, these are the ones with the tie. So nitrogen has 7 protons and neon has 10 protons. So that will help me determine the Zeph value. Okay. Now, when we're looking at the most electronegative element, electronegativity is the atom's ability to attract electrons towards itself in a bond. And so we're going to be looking for atoms that are small in principal quantum number and have the highest Zeph, the most nuclear attraction, which comes from having more protons. So our instinct, and what a lot of you chose, was neon, because neon has the only 2 energy levels and the most positive protons. But this is kind of tricky because neon is a noble gas. Noble gases do not like to bond, and so they break the pattern for electronegativity. Basically, the noble gases we think of as having an electronegativity of 0. So then the most electronegative choice, knowing that neon breaks the pattern, is going to be nitrogen. So letter A, nitrogen, for number 3, because it's the smallest and it has the most, well, really we just then care about the smallest, because if we toss this guy out, then all I'm comparing is the energy level. Okay, and then which element has the smallest first ionization energy? Ionization energy is the energy needed to remove an electron from the atom. And so if we have a small ionization energy, that means it's the easiest to remove. And so I'm, again, going to look at the energy levels. Neon is in the mix here, but we know that it's going to be easier to steal from a big fat atom where its electrons have more distance. If the electrons are far away from the positive nucleus, there's less electrostatic or Coulombic attraction, so it's easier to remove that electron. So in this case, rubidium, letter D, for rubidium is our best choice because it is the largest principal quantum number. Overall, we did really great on this last page. So if you have any questions about any problems you missed here, feel free to talk to me during office hours. Let's just talk about number 10, which contains exactly 2 unpaired electrons. Well, we know we can look at the farthest orbital and sublevel for the unpaired electrons. So sulfur ends with 3p4, calcium ends with 4s2, gallium is 4p1. Antimony is 6p3 and bromine is 4p5. And so we want exactly 2 unpaired electrons. Well, for the p orbitals, we would see something like this. I see 2 unpaired. That's a good sign. S only has 1 orbit, so those are paired, so he's out. 4p1, I just see 1 unpaired. 6p3, 1, 2, 3, I see 3 unpaired. There's 1 unpaired. And then 4p5, 1, 2, 3, 4, 5, just 1 unpaired. So sulfur, letter A, is our best choice for number 10. All right, so we have chlorine and Cl-. Most of us were strong on the electron configurations. You could have done the full 1s2, 2s2, 2p6, 3s2, 3p5, or the abbreviated bracket with neon in the brackets and then colon and then 3s2, 3p5 for regular chlorine. Chlorine minus is the exact same except in ending in 3p5, it is 3p6 because it gained 1 electron, that negative charge. So we just put that extra electron in that 3p sublevel. That's all we do. Okay, letter II. Explain why the radius of Cl- is larger than the radius for chlorine. So first of all, if the AP exam tells you that something is larger than something else, They are not lying to you. That is the truth. So they are telling you, they're not saying which is larger. They are saying the Cl minus is larger. You just have to explain why. So here's what we know. We know if you picture the rings, they both have 17 protons, and they have these rings of electrons. Kind of made that a little close. One, two, three. My chlorine, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. This guy looks exactly the same. So this is Cl, this is Cl minus. 2, 3, 4, 5, 6. And here's the difference right here, an 8th electron in that outer ring. So here's what we know. This guy has an extra electron added. So in the 3p sublevel, chlorine looks like this, and Cl minus has this extra electron, which means we have extra electron-electron repulsions, which means this electron cloud out here has to expand slightly. So maybe it gets a little bit bigger around the edges. So the Cl minus electron cloud is larger than the chlorine because it gained an electron and there's added electron-electron repulsions. Okay, make sure you explain why added electron-electron repulsions would make it larger. It's because the electron cloud expands, and I was looking for that phrase, electron-electron repulsions. And then lastly, which ones will be attracted to a magnetic field? Well, here's my Cl one more time in that 3p sublevel, and here's my Cl minus. What I see is an unpaired electron, and we know if there's an unpaired electron, it is paramagnetic, which means it is attracted to a magnetic field. No unpaired electrons, like Cl minus, means diamagnetic. Magnetism goes to di, so it is not magnetic. So the regular neutral chlorine would be attracted to a magnetic field. All right, letter B. Cl minus is isoelectronic, same number of electrons with argon. From which species is it easier to remove an electron? Well, here's what I know. Both of them have the principal quantum number of 3, or 3 energy levels, right? They end with 3p. Chlorine has 17 protons. Argon has 18 protons, okay? And even though it's Cl minus, it still has 17 protons. So yes, it has an extra electron, giving it the same number of electrons as argon, but the number of protons are different. And so we are only looking at protons because the energy levels are the same. What I see is argon has more protons, which means more core nuclear charge, which means a higher Zeph. And so because argon has a higher Zeph, it means it takes more energy to remove an electron. There's more electrostatic or Coulombic attraction, so it takes more to remove an electron. So I would say for easier to remove an electron, chlorine minus would be easier because lower Zeph. So it has a lower ionization energy. All right, just a couple of things. Here, our calculations were good. We were looking for the frequency, and remember to go from nanometers to meters. We know that 1 meter is equal to 10 to the 9th nanometers. So we're taking this number and dividing it by 10 to the 9th. Should have gotten 4.95 times 10 to the negative 7th meters for your wavelength. So then we can plug in and solve for the speed of light. And then here we can use our E equals h times the frequency. All of these should have had 3 sig figs based off the numbers provided. All right, and then we have hydrogen, and it has a transition from energy level 6, so far away from the nucleus, down to energy level 2, closer to the nucleus. Here, when we go from essentially what's going to happen is for this electron to go from close up high, it absorbs energy, and when it falls back down, it's going to give off energy. So this one we are emitting. You could have explained that by saying when it goes from high to low, it gives off energy, or that we had to put in energy for it to get to that n equals 6, so then it releases it when it falls back down. Some of you chose to use the equation. That is totally fine. It was not provided to you, so you had to memorize it, but this was more a conceptual question. You did not need to actually calculate and show me if it was positive or negative to prove it. You just needed to understand that from high to low will give off energy. And then this one, we needed to use two equations. They gave me the energy, so we needed to solve for the frequency, and then using that frequency, we were able to solve for the wavelength and put it back into nanometers because they asked for nanometers. All right, most of us, again, we're strong with the electron configurations for magnesium and argon. So then let's look at B. In terms of these configurations, talk about the first and second ionization energies of magnesium being lower. And then why is the third one much larger? So let's first start by talking about the first and second. Well, when we're comparing magnesium and argon, they're both in that third energy level, right? 3s and 3p. So then when it's a tie, we look at the number of protons. Magnesium has 12 and argon has 18. So this guy, argon, has higher Zeph. So when removing an electron from argon, there's more attraction to the nucleus because there's a stronger nuclear charge. So it has more electrostatic attraction, so it takes more energy to remove the first electron from argon than it does magnesium. Same with the second electron. So now I'm taking a second electron away. It takes more because, again, still more protons. Here is the issue. For magnesium, 12 protons. Magnesium looks like this. If I take away this first electron, I take away this second electron. Now when I take away the third electron, I am taking one from this inner ring. So now when we're talking about the third ionization energy, we should be talking about core electrons versus valence electrons. We see a big jump from magnesium's I2 to I3 because when we go to take the third electron, we are taking a core electron, which is closer to the nucleus. Whereas with argon, when we take argon, looks like this, 2, 4, 5, 6. There we go. 7, 8. So here's what argon looks like, this guy too and this guy too. When I take the first, he's gone. When I take the second, he's gone. When I take the third for argon, I'm still in that outermost ring. So the distance is to the third energy level, whereas for magnesium's third electron, now we're only going to the second. So for this one, when I'm talking about the third ionization energy, I was looking for you to say that we are now taking a core electron in magnesium, which is much closer to the nucleus. Less distance means more Coulombic attraction, which means it's harder to remove. Whereas argon, the third electron, is still a valence electron, so it has the original distance from the nucleus. And lastly, I want this compound unknown Q bonded with chlorine. Same idea here. I see a big jump from I1 to I2, which tells me Q must have one valence electron. If Q has one valence electron, it means it's likely to form a positive 1 charge. Chlorine is likely to form a -1 charge, right? It's in that second to last column. So Q is likely to give away an electron. Chlorine is likely to gain an electron. And so when we see what ratio do we need of these to make them neutral, or like in regular chem, I say when we crisscross, we get QCl. Some of you noticed that it was an alkali metal, something like lithium or sodium or potassium, but if you wrote NaCl or LiCl, I wasn't giving you enough information to differentiate if it was sodium, potassium, lithium, things like that, right, based off this information. So all I was asking, what is the compound when Q bonds with chlorine? Don't tell me what Q is, just tell me what the ratio or the formula would be. And in this case, I would need 1 Q with 1 chlorine to make the chemical neutral. All right, finish up those square root curve. If there's any that I skipped over that you need some help with or want me to explain again, come on into office hours before you turn it in.